going to do out some calculations for Lugol's solution lab. And I'm going to be just doing one run of the hexane layer and one run of the water layer for, this is for sample A. You're going to have to do two of them and take the average. So just read through the calculation sheet. It tells you everything that you need to do. All I'm doing is showing you what it says. So you should be able to work it through. So you're gonna have this calculation, but you're also gonna have a second one, and you're gonna have to take the average of those two. Okay, so how this works is, for after titrating the hexane layer, we used 5.74 mils, or 0.00574 liters of the thiosulfate solution, which had this concentration. So here are the moles of so the volume times the concentration gives us moles of the thiosulfate. And then according to the reactions that you see in the lab report, it says that moles of iodine are, it's 2 to 1, or 1 to 2, I guess, for iodine. So we just take this number we just have in moles and divide by 2. And it gives us the moles of the iodine. Then to find the concentration of the iodine in the hexane that we titrated, we used 3 mils of the hexane. So it's this many moles divided by the volume. So this is the iodine that was present in the hexane layer to start. Now, this is an equation that's given in the lab as well, that the iodine in the water layer must be equal to the iodine in the hexane layer divided by 34. That has just been found to be true. So we're using that. So now that we found the iodine in the hexane layer, we now find the iodine in the water layer indirectly by just taking that value from above, divide by 34, and there we go. So that's our first data point. We're going to use that a lot later, but that's the first one. So that's the only reason we have to titrate the hexane layer, is to get here. We find this one first, but we're really just finding, what we're after is the iodine in the water layer that we find indirectly. Okay. All right, now we find the triiodide in the water. That's the next thing that we're after. We're finding terms that we're going to be using in the KC calculation at the very end. So we titrate the water layer. Well, we do the exact same thing. You see the math is the same, moles of the thiosulfate, but here we have this is the volume that was used, times the concentration of the thiosulfate. Here are the moles of the thiosulfate. Now the difference here in the water layer is that there's also there's iodine and I3 minus that are present, so we find the moles of both together. So that's going to be equal to the moles of the thiosulfate divided by 2, and that gives us the moles of not only the iodine but the triiodide. Both of them are together, and we don't know how much of each there is. That's we're going to figure that out in a moment. So the concentration of these together is equal to this number of moles divided by the volume that we used, which was 3 mils. And here's our concentration. But this on its own would be more or less useless to us because unless we can separate them. We don't know, maybe there's a really small amount of this and a large amount of this, or vice versa. We don't know, or it may be equal amounts. We don't know. So what we do, we want to find the triiodide ion concentration in water. Well, that's going to be equal to the iodine plus the triiodide, both in water. That's what we just found, this value here. But then we found the iodine in water, or aqueous iodine, from earlier. This was done indirectly on the first page. That was right here. So what we're going to do is take the value that we just found. We're going to subtract off what we know from an indirect route, and this must be the concentration of the triiodide that's in solution, in the aqueous solution. Okay, so we're almost there. Now we need to know the concentration, the initial concentration of the iodide. Well, it was 0.1, but then we took 5 mils of it and diluted it to 13. So this is the initial concentration of the iodide. So, and then at equilibrium, when the reaction is done, we have the initial minus the triiodide, because all of the triiodide came from the iodide, if you look at the reactions, and it was a 1-to-1 reaction. So if there's this much triiodide, it must have been made from the iodide. So we have to subtract off what we found from the iodide, and this is how much of the iodide is left by concentration. Now we have it all. Kc is the triiodide divided by the iodine and divided by the iodide. So we went through this whole thing to get these three numbers. We put them in, and for the first one I get 913 for the Kc. It's a little high, but it's going to be in the hundreds. So I say a little high from what I know to be the actual value, but that's fine for what we have here. So what you want to do is do the other value and the other volumes, and then come up with the average rather than just doing one of the titrations for each the H. So you want to do H2 and W2 for sample A, and then you want to do H1, H2, W1, and W2 for sample B.